Hi and welcome to week 15. So this is the 30-week Leaving Cert Ordinary Level Maths Countdown from TheMathsTutor.ie. As always, the full countdown is available to the full members on the TheMathsTutor.ie website, and there's loads of videos there to help you with each of these topics in your revision. These lessons, we make a couple of videos available to everyone, so they're going to appear in the chat. So we have two videos this week. The first one is on using Venn diagrams in probability. So we're going to be looking at a question later. So we're going to see our Venn diagrams that come up in sets and how we can use those to calculate probabilities. The second video that we're making available this week is random selections from a population. So where we can look at how we can calculate probabilities when we're given different information. So this week, obviously, we're going to be looking at probability, and there's a couple of things that we have to be aware of before we start doing this week's questions. So the first thing is, if we come across the word or in probability. So if it says, I want the probability of doing this or this, then I'm going to be looking at adding together probabilities. And if I see a question that says do this and this, then I'm going to be looking at multiplying probabilities. So when I see the word or, I'm going to be saying that means I need to add. And if I see the word and, that tells me I'm going to need to multiply. So we're just going to keep an eye out for those in the phrasing of our questions. There's something else that we need to be aware of then. So the next thing we need to be aware of is this term mutually exclusive. So the term mutually exclusive means that they cannot occur at the same time. Now, what we mean by that is when we're carrying out experiments, we're looking at the outcomes of those experiments. And sometimes we can get more than one outcome occurring at the same time. So, for example, if I flip a coin, I could get a head or I could get a tail, but I cannot get a head and a tail together at the same time. So head and tail are mutually exclusive. And likewise, if I was to pick a card from a standard pack of playing cards, I could pick a red or I could pick a black, but I cannot pick a card that is both red and black at the same time. So the color of the card is mutually exclusive. But I could pick a red queen. So there are two red queens in the pack of cards. So the card being red and the card being a queen are not mutually exclusive. So if they cannot occur at the same time, we describe them as mutually exclusive, and we say the probability of A or B occurring is just going to be the probability of the first one plus the probability of the second one. So that's what we were saying. We've seen the word or, so we know that we're going to add them together. But if they're not mutually exclusive, so now suddenly they can occur at the same time. So this is our example. Like we said, we could pick a card that is both red and is a queen. So then this means they can occur at the same time. And if I want to work out the probability of getting something like a red card or a queen at the same time can occur, so that means that we need to take one other thing into account. So it's the probability of A plus the probability of B. So the probability of the first event plus the probability of the second event, and we have to be adding them together because we have that word or there. But when we do this, because they can occur at the same time, we've counted the overlap between them twice. So we counted them happening together in A and we counted them happening together in B, as in I counted the red queens when I was counting the red cards and I counted the red queens when I was counting the queens. So what we have to do is we subtract the overlap. So that means that we're only going to be counting the overlap once instead of counting it twice. And this is called the intersection or the overlap between the two. So we're going to see a couple of questions, some of which will be mutually exclusive and some of which will not be mutually exclusive. So if we're asked for things this or this, we need to just have a look at the scenario and determine, can these events happen at the same time or not? And that's going to determine whether we're going to just add our probabilities or add our probabilities and take away the overlap as well. So we just need to keep an eye on the way that the question is phrased. The other thing that we have to look at before we start into the questions is something called a sample space. So when we're talking about a sample space, this is where we list all the possible outcomes. So when we want to list all the possible outcomes of an experiment, we could just write them down. So it might be something like, I'm going to flip a coin and I'm going to roll a dice at the same time. And I'm going to say I got a head on the coin and I got a 1 on the die. So that'd be H1. Or I could have gotten a tail and the number 5, so that'd be T5. So that would be literally just listing out all of my outcomes. Or we could do something called a two-way table, and we'll see a two-way table in our first question here, our first example. So when we have a two-way table, we're going to have one of the outcomes on the top, the other on the side, and then the full outcomes in the middle. So from one piece of the experiment on the top, one piece of the experiment on the side, and all of the outcomes together. But if I have more than two things occurring, we might have to have something called a tree diagram. And when we're dealing with a tree diagram, we're going to have branches coming out and we'll be filling in the probabilities on those, and we'll see an example of a tree diagram in a question as well. So to start looking at some of the questions today then, we're starting with 2018 paper 2 question 1. So this question says, an experiment consists of throwing two fair standard 6-sided dice and recording the sum of the two numbers shown. Some of the totals are shown in the table. Okay, so it's a fair dice, so both of them are fair, and that means all the outcomes are equally likely to come up, and we're recording the sum of the two numbers. So the sum of the two numbers means we're adding together the outcomes from each of the die. So die is the singular, so if I only have one, I have a die, and if I have more than one, we have dice. So we can see here that we've listed the outcomes from die 1 up at the top, so we could get a 1, 2, 3, 4, 5, or 6, and the same down the side for die 2, a 1, 2, 3, 4, 5, or 6. So if we take an example, so if I take this number 7 here, this was that we rolled a 5 on die 1 and a 2 on die 2, and we add those together, so 5 and 2 means we have a total of 7. So they filled in most of this sample space for me. So this is our sample space where we're going to be listing all of our possible outcomes, and it's a two-way table because two things are happening here, die 1 and die 2, and we have the outcomes of those individually, and then we're going to have this sample space showing us all of our possible outcomes. So this is the sample space showing all the possible outcomes. So there's a couple of blanks that we need to fill in. So to fill in this square here, we can see we have a 3 on die 1 and a 4 on die 2, so that's a total of 7. For this one here, we have a 4 on die 1 and a 4 on die 2, so that's a total of 8. For this one here, we have a 2 and a 5, which is a 7. For here, we have a 5 and a 5, which is a 10. For here, we have a 6 and a 1, which is a 7. And for the last one over here, a 6 and a 6 is a 12. So now we've completed our table. We've filled in all of our possible outcomes. So part 2 of this question says, find the probability of getting a total of 7 or 11. And they've put the word or in bold there because that's the piece that I need to look at and say, okay, I'm seeing the word or, I'm going to be adding together my probabilities. So when I look at this two-way table or my sample space, I want to see, can a 7 and an 11 occur at the same time? So they can't. So that means that 7 and 11 are mutually exclusive. So they are mutually exclusive. So that means they cannot occur at the same time. So the probability of 7 or 11 is equal to the probability of 7 plus the probability of 11. So there's no overlap between them. So the probability of getting a 7, there's 1, 2, 3, 4, 5, 6 sevens. Out of, when I count up all the possible outcomes in this sample space, there are 36 possible outcomes. plus the probability of getting 11. There are 2 11s, so that's 2 out of 36. So when I put that into my calculator, I'm going to get an answer of 2/9. So there's an example of something that is mutually exclusive. I cannot get those two outcomes occurring together, so all we're going to do is add together their probabilities. For part 3, it says find the probability of getting a total which is a prime number. So to do this, we have to remember what a prime number is. So a prime number is a number that only has 2 factors. The factors are going to be itself and 1, so it won't have any other factors. So we're going to mark which numbers in our sample space are prime. So 2 is a prime number, it's only 2 multiplied by 1. 3 is a prime number, 3 1s. 4 isn't because we've got 2 2s. 5 is because it's only 5 1s. 6 isn't because it could be 3 2s. 7 is, so it's just 7 1s. 8 isn't because we have 4 2s. 9 isn't because it's 3 3s. 10 isn't because it's 5 2s. And 11 is, but 12 isn't because it's 6 2s. So now we've highlighted all the sample space prime numbers. Now you'll notice that I didn't highlight anything up here at the top under die 1 or anything here on the side under die 2. They're not part of my sample space, so they're not part of my possible outcomes. It's only these ones in here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 prime numbers. So the probability of getting a prime number is 15 out of 36. And when we put that into our calculator, it tidies up to give 5/12. And I'm going to leave all my answers for this part as fractions, so they're nice fractions. We don't have to convert them to decimals. It doesn't ask me to, so we can leave them as fractions. The part B of this question doesn't give us a sample space, so this is all written in words. It says a car distributor sells Ford cars and Renault cars. It has 30 cars for sale on a particular day. 18 are Ford cars and 12 are Renault cars. So nothing else is listed, so there's only Ford cars and Renault cars making up the 30 cars. 7 of the Ford cars are red and 4 of the Renault cars are red. One of the 30 cars is chosen at random. What is the probability that the car chosen is a Ford or a car which is not red? So or again is in bold, so that's telling us we're looking at adding, but this time we need to determine are Ford and red mutually exclusive? Ford and not red, excuse me. So we're looking for not red and Ford. So I was told that 7 of the Ford cars are red and there were 18 Ford cars altogether. So that means there are definitely Ford cars that are not red. So these are not mutually exclusive. So they can occur at the same time. So when we want to calculate the probability of Ford or not red, we're going to say it's the probability of Ford plus the probability of not red minus the probability of the not red Fords. So when we calculate the probability of Ford, we're going to include all the not red Fords. When we calculate the probability of not red, we're going to include all the not red Fords. So we'll have counted them twice because they're not mutually exclusive. There is this overlap or intersection, so we're going to have to take away that part. So the probability of getting a Ford. So there are 18 Ford cars out of 30. So we have 18 out of 30 is the probability it's a Ford. The probability that it's not red. So we can see that the red cars, there were 7 red Fords and 4 red Renaults, so that's 11. And there were 30 altogether, which means the not red is going to be 19. So we have 19 over 30. Now, if we added these two fractions together, so if we hadn't taken into account that these were not mutually exclusive, we would be getting a fraction that's greater than 1. And the probability scale runs from 0 to 1. So we're never going to get an answer that's greater than 1. So that would tell you go back and look for that intersection. So how many not red Fords are there? So there's 18 Fords and 7 of them are red. So when we subtract that, there means there's 11 not read Fords. So the 11 not read Fords we counted when we counted all the Fords, and we counted them when we counted all the not read Fords, but we only want to count them once, so we're going to subtract the overlap between them. And when we put that into our calculator, we're going to get 26 out of 30, and that's going to tidy up to give us 13 out of 15. So in that second part of that question, we see an example where they're not mutually exclusive, so we're going to have to take that overlap into account. Okay, so the next question we're going to look at has a Venn diagram in it. So this is 2016 paper 2, question 1. It says a survey of 168 people was carried out. Participants were asked whether they owned a cat or a dog, and some of the results are recorded in the Venn diagram below. So just to remind us of our Venn diagram, this whole circle here represents everyone who has a cat, and this whole circle here represents everyone who has a dog. So I can see that there's 2 figures filled in for dogs so far. There's 48 people here who have a dog only, and there are 64 people here who have both a dog and a cat. So this is our intersection or our overlap. So these are not mutually exclusive events. So some of the results are filled in. I can see I haven't been told how many people only have a cat. But in the first part of this question, it says of those surveyed, 19 people did not own either a cat or a dog. So when they don't own either, they don't go in either of the circles, but they go in our rectangle of U, our universal set, which is all 168 people. So they go outside the circles is going to be the number 19. So now to figure out how many had a cat only, we're going to add together the numbers that are already filled in, which is 64 plus 48 plus 19. And when we add those together, we get 131. So there's 131 people already filled into this Venn diagram, but it told us that there was 168 people in the survey altogether. So we subtract 168, take away the 131, and that's going to give us 37 had a cat only. And we fill in that number here. So when we're filling in this Venn diagram, we're filling in the number of people in each of these sections. A person is chosen at random from those surveyed. What is the probability that the person owned both a cat and a dog? So both a cat and a dog, that's our overlap or our intersection. So when I look at that, that's these 64 people here in the middle. So we're going to say the probability of both cat and dog is going to be that overlap of 64 out of 168. And again, we'll tidy that up on our calculator, and that gives us 8 out of 21. So when I have a Venn diagram, I don't need to worry as much about this mutually exclusive. Am I adding? Am I multiplying? Because I'm reading these things out of this Venn diagram that's given to me that I have filled in. The third part says, what percentage of the people surveyed owned one animal only? So this is only a cat or only dog. So we're not interested in the overlap this time, and we're not interested in the 19 people out here who didn't own either of them. So the probability of one only, so there's no overlap because we're looking at one only. So that's going to be 37 out of the 168 plus 48 out of the 168. And when we add those together, we're going to get a fraction. But it asks me to give my answer correct to one decimal place as a percentage. So what percentage of these people? So when we add these together, we get 85 out of 168. And we change that to a percentage by multiplying a fraction by 100 or by 100 over 1. And to one decimal place, that gives 50.6% of the people surveyed had only one of a cat or a dog. The second part of this question then, this is our tree diagram. So we said when we have a tree diagram, we're going to have our branches coming out. So this says Mandy wants to buy a ticket to the theatre. She can choose a ticket in the balcony or the stalls. So there's our first division. We can see that she could either go for the balcony or she could go for the stalls. So we've got our first division. Mandy can go on a Monday, a Wednesday, or a Friday. And that's the same whether she picks the balcony or the stalls. They just haven't completed this tree diagram. They want me to fill in the rest of it. For an extra charge, she can choose a VIP ticket where she will meet the band, or she can choose the show only. So for each of these, we're going to have a V and an O. So each of these could be a VIP or just the show. So we have a V and an O coming out of each of our branches. So now we have all of our branches filled in. So it says complete the tree diagram below and hence or otherwise find the probability that Mandy chooses a VIP ticket on a Wednesday. So we want to know the probability that she gets a VIP ticket on a Wednesday. So what are the outcomes? So we haven't listed our sample space yet. So what are these outcomes? So we need to work out getting to this V here. This was that she chose the balcony on a Monday and a VIP ticket. So that's B, M, V. This one is the balcony on a Monday, but the show only. To get to this branch, we follow the balcony on a Wednesday and the VIP. And to get to this branch, the balcony on a Wednesday with the show only. The balcony on a Friday with the VIP, or the balcony on a Friday with the show only. And then we switch to the stalls. So the stalls Monday VIP, the stalls Monday with the show only, the stalls Wednesday VIP, the stalls Wednesday show only, the stalls Friday VIP, not W, stalls Friday VIP, or the stalls Friday show only. So we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outcomes here. And what we're looking at, it says you may assume that all choices are equally likely. Now that doesn't always happen. So sometimes they're going to give us different probabilities, but what it means that I'm equally likely to choose the balcony as the stalls. So that means the probability of a balcony for Mandy is a half, and the probability of the stalls is also a half. And then she's equally likely to go on a Monday, a Wednesday, or a Friday. So each of these is going to be a third. And that's the same probabilities down here. And she's equally likely to choose the VIP experience or the show only. So each of these is going to be a half. So we'll often have to fill in our probabilities on our branches. So that's what we're showing here in this lesson. But in this case, we can just assume that they're all equally likely. So what I could do to work out the probability of the balcony and a Monday and a VIP would mean multiply. So I'd be saying a half by a third by a half. So that would be 1 by 1 by 1 on my top line is 1, and 2 by 3 by 2 is 12. But because they're all equally likely, each of these is going to have exactly the same probability because this is 1 out of my 12 possible outcomes. So we said there was 12 possible outcomes here and they're all equally likely, so 1 out of 12. But if these fractions were different on my tree diagram, then I would have to do this method of working out my fractions and multiplying to work out what is the probability of getting to the end of that branch. So what I'm looking at here is find the probability that Mandy chooses a VIP ticket on a Wednesday. So I need a W and a V, so I have 1 there and I have 1 there. So that's 2 out of my 12 options, which is a probability of 1/6. And that's how we list all our possible outcomes and make our sample space by using a tree diagram. And the last question we're going to look at is another question on a Venn diagram. So this is from 2012, paper 2, question 2. So this one we have to fill in all of the Venn diagram. And this question, we just need to remember what's a pack of playing cards. So we're familiar with coins, heads and tails. We're familiar with the dice, so there's 6 sides on the cube. But when we're dealing with a pack of playing cards, just to remember that there are 52 playing cards. You have 4 different suits in them. 2 of them are black and 2 of them are red. So we've 26 black and 26 red and 13 of each of those suits. So 13 diamonds, 13 spades, 13 clubs and 13 hearts. And then that we have something called picture cards. So these are your kings, your queens and your jacks. And this is that there are how many we're going to be filling in. So it says in the Venn diagram below, the universal set is a normal deck of 52 playing cards. The 2 sets shown represents the clubs and the picture cards, the kings, the queens and the jacks. So show on the diagram the number of elements in each region. So clubs, there are 13 clubs. Picture cards, there's going to be the jack, the queen and the king of hearts, of spades, of diamonds and of clubs. So that means that there's 12 of them. But we have an overlap. So the overlap here is going to be the club picture cards. So these are not mutually exclusive events. So this is what we were explaining, that I can pick a card that is both a club and a picture card because I have the king of clubs, the queen of clubs and the jack of clubs. So there's 3 in the overlap. So I'm going to fill in the 3 in the overlap first. The whole oval here that's labelled as clubs has to add up to 13. So we have 3 filled in already, which means we're going to fill in 10 into this section. And the whole oval here marked picture cards has to add up to 12. We've 3 in already, which means we're going to have 9 other picture cards. Now, when we add all these together, we're going to be saying, right, we have 10 plus 3 plus 9. So that adds up to give 22. And there's 52 playing cards all together, which means there's 30 cards that we haven't talked about. And they go out here in this section, which are the ones that are not clubs or not picture cards. So the next part says a card is drawn from a pack of 52. Find the probability that the card drawn is the king of clubs. Well, that's just one card out of the 52, so the king of clubs is 1 out of 52. Whereas the last part says a card is drawn from a pack of 52 cards. Find the probability that the card drawn is a club or a picture card. Right, so if I want to do this from my Venn diagram, this means that I'm looking at everything that's in these 2 ovals. These are all my clubs and picture cards. So if I use the Venn diagram, I'm going to say that's 10 plus 3 plus 9, each out of 52, which gives me 22 out of 52, and that would tidy up on my calculator to give me 11 out of 26. So when I'm using my Venn diagram, I'm just going to be saying it's these 3 sections that we've highlighted. So 10 out of 52 and 3 out of 52 and 9 out of 52. But if I wasn't using my Venn diagram, so we would have to say these are not mutually exclusive. Which means the probability of club or picture is the probability of a club plus the probability of a picture card minus the overlap. So minus the probability of the club pictures, because we'll have counted those twice. So the probability of a club is 13 out of 52, plus the probability of a picture card is 12 out of 52, minus the overlap was 3 out of 52. And when we add those together, we get 22 out of 52, which is 11 out of 26. So that's showing you a couple of examples of working out probabilities where we have this or this happening, and we see that it depends on whether we have mutually exclusive events or not mutually exclusive events, and how we can get a sample space. So using either a two-way table or using a tree diagram. So hopefully you found this lesson to be useful, and don't forget there are still 2 videos there for you to look at. So one on random selections and one on practicing using your Venn diagrams. Thanks.